Hey there, everyone. My name is Ryan Schul. Welcome to my data science channel. So in the project today, I want to take a look at potential places where we can open a new Starbucks restaurant. Okay, originally I was thinking about where could we open Taco Bell's. I like Taco Bell, but Taco Bell honestly is like kind of a little bit low class. I was thinking, okay, maybe something a little bit higher end, a little bit Chipotle-ish, and I could certainly do that, but I thought, let me just level it up to a whole nother level. Let's look at Starbucks. I think it's pretty refined type of restaurant, very, very engaging type of experience, and it's more of a gentrified type of um, interaction too. When you see Starbucks come into a neighborhood that is a little bit dilapidated and a little bit kind of depleted of resources. If you see a Starbucks come in, it might mean the neighborhood is turning around and getting a new injection of adrenaline boosted into the local neighborhood system, right? So I decided to settle for Starbucks. So I went ahead and put together some analysis. And I want to share my findings with you right here, right now. So why does this matter? This basically gives us a granular estimate, not just a yes or no, are we going to be profitable or not profitable, but all kinds of scenarios in between. We're going to look at some regression analyses and some classification experiments, and we're going to see how things shake out. Okay, this is going to enable ranking of candidates for different locations based by profitability, overall profit potential for different restaurants opening up in different neighborhoods, right? Helps with budgeting, forecasting, scenario planning, understanding foot traffic. Increases by 10%, what kind of impact is that going to have? If we lose foot traffic by 10%, what kind of impact will that have, right? What if scenarios? What if this happens? What if that happens? What kind of outcome can we expect? Why does this matter? It's easy for executives or real estate teams to act on this information. It allows for building decision support tools and really quantifying decision making, right? And we're looking at different scenarios where we can actually harness different insights and produce um, different insights into different scenarios and make intelligent, informed decisions based on quantifiable material, right? That's what we're looking at here. And we can model for risk tolerance and adjust for profitability and adjust based on different thresholds, 50% confidence, 70% confident. Like, how confident are you, right? And how much does this matter? I think we're going to look at things like that. So we have to gather and prepare data, looking at existing Starbucks store data, latitude, longitude, so we can see where they are dispersed geographically, sales, customer traffic. Is it urban, suburban? Is it drive-through? Location attributes, foot traffic, population density, demographics, labor costs, competitive presence, right? Do we have Dunkin' Donuts right across the street or half mile down the street, quarter mile, 2 miles down the street? Where are we located compared to our competitors? And what kind of amenities are nearby? Are there office buildings? Are there colleges? Are there malls? Are there transit stations? Are there shopping centers, right? That's what we have to try to identify and understand. So I looked around for some information. I found some data over here on this website. You can take a look. It was somewhat informative and a little bit useful, but not really. It's really lacking a lot of information. This has Starbucks locations worldwide. It has mostly lat long coordinates and a couple other very basic information, but it's really lacking in a lot of things. It doesn't have like city, state, population density, demographics, things like this. And it certainly doesn't have any kind of like labor costs, unemployment rate, competitor density, things like this, right? These are things that Starbucks has and it collects, but they hold it tight to the vest or close to the vest, whatever the term is. They're not going to expose that. They're not going to give that to you, right? So I came up with realistic estimates of what these should be. I think it will serve the purpose here. I think it's going to be pretty meaningful, pretty realistic. Hopefully it hits the point. If not, I mean, we could dial it in, dial it down a little bit, dial it up a little bit. I don't work for Starbucks, so I don't have access to this information. And if I did, it would be personal and confidential. I certainly couldn't share it in a public domain like this right here, YouTube. So we're going to make up some hypotheticals, but again, this can be realistic and try to create a scenario that we can analyze and derive some utility from, some satisfaction from, okay? So that's what it is. It's made up data, but it should represent actual numerics and actual quantifiable numbers that Starbucks would have, okay? Again, I don't work there and I don't really care what Starbucks is doing. I'm trying to recreate a scenario that is hypothetical, but mostly realistic. So we have a few cities here and located in a couple states, lat long coordinates. I am going to create details of city, state, lat longs, population density, median income, demographics like educational level, um, percent of residents under 35 versus over 35, square footage of the restaurant, labor costs, unemployment rate, competitor density, and nearby amenities. And I'm going to create multipliers for each one of these variables over here, okay? So let me hit Control Enter to create the data frame. You'll see what it looks like, city, state, lat long, demographics over under 35, commercial rent per square footage, labor costs, unemployment, and so on and so forth, okay? So let's go ahead and create our first machine learning algorithm. So I'm going to use a regression algorithm. We have city, state here, which are not numerical, okay? So we have to take these and label and code these, or one-hot encode or categorical encode these, right? We have to get these labels or text or string into some type of numerical representation. So the computer knows lat long, it knows foot traffic, it knows numbers, anything that's numeric, the model is going to know. It's not going to know what New York is, and it's not going to know the abbreviation for New York is NY. It doesn't know San Francisco, it doesn't know CA. So I'm going to create some synthetic label encoding just to represent these strings right here as numbers, okay? And again, there's three ways to do this. Label encoding, one-hot encoding, and categorical encoding, and there's pros and cons to each of these. I have a whole nother video dedicated just to encoding, so you can check that out on my site. So just trust me right here, we're going to encode these. I'm going to feed that into a random forest regressor, and I'm going to set number of estimators to 50. We're going to go down number 50 levels. Maximum depth is 10. Maximum feature square root. The number of jobs is -1, and the random state is 42. So we start randomly and we end up randomly. But again, the way the random forest works is we're looking at Gini impurities. If the impurity is increasing, we stop going down this path and we go into an adjacent path. And if that is increasing in impurity, we stop that and go into an adjacent path. We want the impurities to decrease over time so we get more and more realistic predictions for our outcomes. So the overall R squared is 0.87. So 87% of the time, we're making accurate predictions into the future. Unfortunately, about 13% of the time, it's not going to be accurate, right? It's going to be just a random guess because the computer is trying to estimate and figure out what is most likely going to happen, but it can't do this with 100% mathematical precision. There's a little bit of deviance, there's divergence, there's a little bit of confusion in the algorithm's ability to make predictions, but 87% is fairly accurate, right? We like to get close to 0.9. Over 0.9 is better. High 0.9 is 0.97, 98, 99 is very good. If you get too perfect, that's 0.9999, you might be overfitting the data, and you might have to use a couple techniques to sort of like scale back the way that the algorithm is working, so it doesn't tend to overfit and learn all the nuances and all the details or all the noise of the system. You want it to learn the major details of some of the minor details, but not every single detail. You want the model basically to learn the system and to make accurate predictions into the future on scenarios that it has not seen yet, right? Because it's going to memorize all the scenarios it's seen. It knows what the inputs are, and if it sees the same inputs, it knows what the outcome is going to be. You want this model to generalize on scenarios that it hasn't seen, but it's pretty close to scenarios that it has seen, and it can make a prediction into the future. So the model has been trained, tested, 87% accurate. Let's say we're going to open a new Starbucks store in New York. This is a lat long coordinate. Foot traffic is 8,000. We're going to say per day, okay? Total population density is 200 and, this is 25,000. So this is probably upstate New York somewhere. Median income for the neighborhood is 85K. Education level is 0.7. 70% of the people have college educations. Percent out of 30 is 0.55. So kind of scaling under 30, not so many older people, more skewed towards lower aged people, younger people. Commercial rent per square foot, labor costs, unemployment, compensation, competitor density, and nearby amenity score, 0.5. Okay, so we have these variables. This is going to be similar to a scenario that we've already seen. It says city, hasn't seen city. Wait, let me try this again. City should be in there. Oh, I think I know what it's doing. Okay, so let me see. So So, okay, let me see. Let me see what this thing did. Think I know why. Display. Okay, so let me see. Whoops. Let me see what the head is looking like now. City. No, that should be fine. City is city, right? For okay, label encoded city. Or is it city? One. Okay, so one is New York. Let's see. One is New York. Yep. And then state is 1 and 5. So state is 5. Okay. So for city, let me see. Something's definitely a little bit weird. I just ran this before, so this should work. Like sometimes I don't understand these things. I literally just tested it before I turned on the recorder and everything was fine. Then you hit record, and of course I don't edit any of these things. So it probably would behoove me to learn how to edit these things. One of these days probably save a lot of time for myself and for you guys, the audience as well. So one of these days I should learn. I have a cheap recorder here, so I'm not even sure I can even edit these things per se. I mean, I think you just hit record and just go. But maybe, let me see. So one hot dummies use PT dummies instead of label encoder. They should use transform instead of match dummies. City state, column encoders. Okay. Column and city state. Well, that's what they had. New York, New York. We go back. New York, New York. Transform. And column states. Okay, let's try that. Game for that. State. Okay, state. Oh, okay. So I think I need that too because you have to label code it. City and state. So so I know that. Let's see what this does. Okay. So the encoding is fine for column city state. If new code, new store code. Should work. Why is this not working? This is city and state. Could not convert to string to quotes. Let me see. Let me see. It's kind of amazing how it works. And then you turn on the recorder and then it doesn't work. So not sure about that, but I did the label encoding. I did the decoding over here. So city, state, everything else is numerical, right? So that is totally fine, but I want those two because that is going to make a difference, right? So if you label encode, I did that. Make sure you apply the same encoder during training. Label encoder, right? We get rid of that. And that is label encoder. Straight. I did that. predicted profit. Okay, so let's get to the bottom of it, and that is going to be that, right? So I coded it. I just don't know why I can't decode it. Let's see. Maybe I feel like new stored col. Coder. Oh, yeah, maybe that's too much. Maybe that's too many encodings and decodings. Let me try this. Okay, got it. I had extra encodings in there. Okay. So anyways, we got 0.87% accuracy. So 87% of the time, we're going to make accurate predictions, 13% of the time. However, it's going to be random or it's going to be a little bit off, but it's going to be pretty close if we're right at the margin. The cutoff for this here is a threshold of 100,000. We're saying if greater than 100,000, we'll open a restaurant or open a new Starbucks. If it's at 100,000, we won't. If it's less than 100,000, we won't. So if it's close, like 105,000 in profit per year after all the expenses, right? This is the net profit after we pay for the raw materials, the resources, the labor, all the 401ks, the salaries, healthcare benefits, vacation, all this for all the employees, all the coffee beans, the transportation, the gas for the shipping, the supply chain management, all this stuff, right? If we have 212,000 net after all the overhead, we are going to go ahead and open a store. That's going to be profitable. So that's what this regression analysis tells us. We trained and tested the model over here using Random Forest Regressor. Okay, so the dependent variable right here is annual profit. What determines annual profit? It's all of these variables. So city, state, latitude, longitude, foot traffic, so on and so forth, except for annual profit, because that's what we're testing for, right? So we're gonna leave off annual profit. We're gonna drop that out and open store. That is the classifier. We're gonna see that in the next step. Are we gonna open the store or not open the store? So we're gonna drop these two from our independent variables and use everything else. So everything from the left of here, right, between the beginning and ending, and we're trying to predict annual profit. 87% accuracy. This says we're going to have $212,000 in profit. If I change one of the variables over here, all of a sudden labor costs goes to $122 per hour. We're going to see this decrease most likely. Control Enter. 209 decreases, not a lot, but decreases a little bit. Comparative density, if this is 4, maybe if I make this 20, we'll see a decrease or increase just a little bit. That's weird. Nearby amenity stores, if it was 0.85, probably decrease, right? 210, 201. So you change these variables over here and the output is going to change, right? That's the whole point. Now let's say we're looking at a classifier. The classifier, we're going to train and test it again. We're looking at an accuracy of 0.94, higher is better. 0.10 is the best. 0.99 is pretty close. 0.94, recall 0.987, 96. So all high nines, very good accuracy, precision, recall F1 score. And you can see the same repeated down here, 93, 94. Recalls a little bit lower here, 74, 99, 96, 82. Overall, very accurate classification technique, right? And again, we're looking at all the independent variables. So all these variables over here, right, except for annual profit and open store. So annual profit is the regression analysis that we're doing here. Annual profit is going to be $201,498 in this case. The classifier is a label. It's binary outcome, yes or no, true or false, on or off, up or down, left or right, whatever the thing is. Open the store or don't open the store. This is a binary outcome right here. So based on all of these random forest classifying models that we trained and tested over here, this is a training, this is a Y training. So the X is all the independent variables, the Y is all the dependent. We are measuring the ability of the model to make predictions based on the X test. So you have the training here. The testing is what we're trying to predict. So the training, I explain to people as training is like if you're a college student, you go to class, you're in lecture, you do the homework, you read a book, that's all you're training. The test is when you take the test, you prove whether you've retained the information, yes or no. Did it sink in? Did you internalize it? Can you regurgitate it? Can you generalize that to new problems? Yes or no? Now we're seeing the same thing over here. Let me see what the heck changed over here because I don't know. Everything was working fine. Don't know what's going on. And of course, I have to go pick up my son from daycare camp because he's in camp now for the summer and I have to get going. But I have to finish this thing because I can't go ahead and do an edit. I have to figure out how to do the edits on this thing one of these days. So soon. I think it's the same thing as before. So New York is the string and it doesn't like strings. I understand that. So the classifier has to label and code everything. But it should have done that over here. That's what the encoding is for. Training, testing, for applying. So wait, let's see. So if I label and code these, new store, classifiers, new store copy. So I'm going to copy that from the original. This is always good practice to copy the original data frame. So if you're making changes on a copy, it's just changes on the copy. If you make changes to the original, then you want to go back. Then you could be in a tight spot. You have to reload the original data and run through the whole analysis again. It's really best practice to copy things over and work from the copy. Then if you make a change accidentally or intentionally, it's not going to affect the original data frame, right? So you're safe. This is just a safer practice over here to do it this way. So let me go ahead and see if I can make the prediction. Okay. So I think I had an extra line in there or two. One thing can mess up the whole analysis, right? So again, the regression, we're looking at numbers. We're looking at a continuous outcome, 201,498. That's very specific, right? Numerics represent a regression type of problem. A classifier is shown in the form of binary outcome, yes, no, on, off, true, false, something like that, or some labeled data. So it can be orange, apple, grapes, banana, pineapple, coconut, something like that. That could be a classifier, right? If you look at an image, classify the image as some type of fruit. It could be a watermelon, doesn't matter, right? Could be large, medium, small, extra large, something like that. That's that size of that shirt or those pants or whatever. That thing is classified as a certain thing. So in this kind of scenario, we're not working with numbers, we're looking at classifiers and we're saying the binary outcome is if we achieve a certain assumed level of success, we will open the store. So we're 96% confident that the store will be successful based on this, not based on this representation, but it goes hand in hand with this analysis, right? So we said the arbitrary limit for success is 100,000. If we can achieve 100,000 net income in profit, we're going to open a store. If we can achieve a certain level of success based on the accuracy, precision, recall, F1 score, this is the ability of the classifier to learn and to make predictions. 96% of the time, we will open the store and we will be successful. 4% of the time, we'll open the store and it won't be successful. That is called the cost of doing business. That's just how it goes sometimes, but 96% of the time, we're going to be successful. So let's go ahead and set up some clustering exercises. And I want to understand how all of these variables based on the annual profit, commercial rent, labor costs, and foot traffic, what is the summary cluster for all of these variables? And we're going to assign a cluster here. There's 5, 4, 8, 9, 7, 6, 2, 0, 4, 3. So we have 10 different clusters. I believe what I set for clusters over here. If I look close, yeah, 10. So you have 10 clusters, starts with 0, goes up to 9. So there's actually cluster 10. This will be cluster 1. They just represent it as a 0. And these are the annual profits for each one. All these clusters are over 100,000, so all these stores are successful. We have the commercial rent per square foot, the labor costs, and the foot traffic. So we have everything clustered together nicely. Let's look at a SHAP plot. SHAP is going to show us two different plots. In the first plot, we see the global features, everything comprehensively. And this is going to tell us on the x-axis how much each feature increased or decreased the model prediction. The color features, red is high, blue is low. So red, you can see on the right-hand side of the median here, blue is low on the left-hand side. Each dot represents one data point, and the population density and foot traffic have the strongest effects, positive or negative. So population density and foot traffic, just because they're elongated the most, foot traffic has an effect on the success of the store, and median income of the store has a success on the store. So you can imagine it makes total sense, right? Look at this, guys. Population density, the greater the x-axis, the longer it is, the more success on the store. Again, high is red, low is blue. So we want to see more dots to the right. High, that's going to guarantee success. There are some to the left, and that's going to offset some of the success, but still, overwhelmingly, we have success. More foot traffic, more success, more median income, more success. So labor cost per hour doesn't really determine the success of the store. Maybe incrementally, if labor cost spikes up a little bit, maybe it's going to have an impact, but essentially it's no impact. Percent of population out of 35, we don't care. Longitude, latitude, we don't care. Competitor density doesn't have an impact. Nearby amenities doesn't have an impact. And sum of score of 5 or greater doesn't have an impact. So we can see here the overall profitability of a store on median is $122,095 per year. Remember, 100K is the cutoff. If we can achieve more than 100K, then we're going to go ahead and build a store. So the second graph tells us that. The first tells us overall comprehensively what's going to determine the success: population density, foot traffic, and median income. The second is more of a local type of analysis, right? The first is global, it's macro analysis. The second is local or micro analysis. The SHAP value impact by model input is affected by each dot, each single prediction, high or low, from the median number right here is 154,026. Population density and foot traffic are the most impactful features. High values are red, low values are blue. Low values push profits down, high values push profits up. Higher values decrease predictive profits, and nearby amenity score has a smaller but positive influence when high. So again, population density, foot traffic, and median income all play an impact on the store, positive or negative. Labor costs, latitude, longitude has no impact. State, college education, and the other features have no impact. So everything comes down to population density. If you understand that well, you will know how successful the store is going to be. Foot traffic in the neighborhood, not necessarily in your store, but you're going to get some collateral effects from more foot traffic. More foot traffic means more business in your store. And median income, if people have more disposable income, they'll spend more at Starbucks. If they're living hand to mouth, you're not going to have as much people shopping in Starbucks, right? So let's look at the Haversine longitude, latitude, distance between these coordinates. And we have the latitude, longitude right here. We're looking at the Haversine distance. Haversine is the curvilinear surface of the Earth, and the distance between longitude, latitudes, and what kind of impact that is going to have, right? So the list of longitude, latitude coordinates for candidates in certain locations impacts the profitability of the store and is a competitor at least 2 miles away from an existing store. That's why we're calculating the Haversine distance. The Haversine is the curvilinear distance on the surface of the Earth between longitude and latitude coordinates. It's not, as the crow flies, it's not like linear as you drive your car. It's curvilinear because it's based on the circumference of the Earth, right? So we're looking at least 2 kilometers away from the existing competitor or another Starbucks store, because we don't want to cannibalize our own business, okay? So if all these things align, all these different features align, and we find a great place to open a store, but there's a Dunkin' Donuts right across the street, or Tim Horton, if you're in Canada, they sell coffee, Tim Horton right across the street, or another Starbucks directly across the street. You walk off the street and you see at Starbucks, you're face to face, facing off at the Starbucks. You might not want to open a Starbucks there. You could cannibalize your own business, right? So we want to find the best locations based on median income, latitude, longitude coordinates, like foot traffic. What was the number one driver over here? Population density, right? If all these align, but you have a competitor right across the street or within 2 kilometers or another Starbucks, that could cannibalize your own business. Within 2 kilometers, you might not want to open a Starbucks there. Now you might, I live in New York City, I've seen Starbucks right across the street from each other, and both are lucrative, both are profitable, right? So it might make sense to do that, but you might want to second guess your decision and just try to look for something that's less cannibalistic and just more profit driven in terms of there's no Starbucks serving this community, so we can open one with a high degree of confidence that the Starbucks is going to be profitable. So I have a map here. If I zoom out a little bit, you can see the locations here. The blue dots represent stores that are recommended to us based on the whole DF filtered data frame that we set up over here. This comes from filtered candidates, which comes from here, all right? Candidate for candidate and candidate coordinates. And the candidate is not too close to a competitor or not too close to another Starbucks store. If you don't meet those criteria, we have the longitude, latitudes. We have a few in Boston. We have several in New York. If I zoom out, you can see some of the other cities that we picked. Chicago. This is Atlanta, Georgia. If I zoom in there, we can see the locations that are being recommended to us based on all the criteria that we looked at. Disposable income, what else? Foot traffic, things like this, right? And is there a competitor across the street? Yes or no? So these are locations that are worth further investigation. These are places we want to, set up a meeting with our colleagues and have a conversation. Does this make sense to you? Does this make sense? Because this makes sense to us. Does it make sense to you? Now we're looking at the clusters that we set up previously in one of the earlier experiments that we ran. Now we're looking at clusters, again, based on longitude, latitude coordinates. And here's New York. I'm going to zoom in on New York. This is where I live. So I would recognize some of these spots right off the top of my head. So Long Island City, that's where I live. So annual profit, 144K. This is cluster 4. Profit, 134K, 199K, and 185 cluster 4. This is cluster 5. Cluster 2, cluster 0, 153,000. So again, this is a starting point for a conversation with some of our colleagues. We'll set up a couple meetings and, pitch to them our findings here. And here's the final map I came up with. This is looking at longitude, latitude, again, annual profit. And in the city, open a store equals 1 if it's green, otherwise it's red. So all these come up red. I can zoom in here and I can look at the stores that are being recommended to us. So Astoria, I can zoom in here. 6.0 in the pop-up. This is, I see the annual profit, 189 profit, and row is city, 6.0. What's the 6.0 represent? Cluster? Row is city, right? Let me look at one thing right here. I think these are clusters, but I'm not totally sure now. Well, they all be the same then. Wait a second. Okay, so I think the clusters are going to different cities. That's what it is. So the clusters are going to different cities. The cluster comes from here. This is in our data frame, right? This is the annual profit. This is the regression analysis that we did initially. This was to open a store, yes or no. 1 means yes, 0 means no. And this is the cluster that falls into, and this cluster comes from, STR comes from previous experiment that we ran over here. And this is based on the k-means fitting. So based on the fitting of those k-means, profitable, this is the data frame called profitability, and it goes into that cluster, okay? And then it's mapped in Foley and Plotly. So this is Houston, this would be cluster 3. So it's just taking all of the cities and assigning these to clusters, whereas in the previous example, it would create different clusters inside the same city, right? So I'm not saying one is right and one is wrong, it's just different methods, different way to skin the cat. We have, just city number 6, and then cluster within the city. Okay, I see. And this is just clusters in the same city with the profitability showing when you zoom in and it pops up in the bubble. So this store is going to make 143,000. That's making 121, 178, 177, and these downtown 212 per year, 200,000 and 183. So we're getting a lot of hits. Maybe we have to increase the threshold beyond 100,000 up to 200,000 if the total profit, the total net profit after all expenses, everything is paid and done for, all the salaries, all the raw materials, all the supply chain management expenses, the rent, everything is paid. If you have 200,000 in profit or more, maybe we should just consider these stores. If you want to saturate the market a little bit more and go over above and beyond, maybe you have a lesser threshold, 150K, but I set the threshold for 100K, and I'm kind of second guessing that. Maybe that's too low. Maybe we need more Maybe we need to amp up that threshold over 200,000 or more. But still, overall good analysis. We know where to open these stores. We have a lot of information here now to start a discussion with the finance team, with the operations team, the real estate team, the accounting team, the tax team, all these teams. We can start to set up some meetings, sit down with these guys, showcase our findings, and get buy-in from them, get feedback from them, and then determine the next steps here. So basically, profit estimation, check. Decision troubleshooting, check. Prioritization, strategic planning. We used regression to predict how much it's going to cost, how much we can make from each store, ranked all locations by profit, and budgeting ROI estimation. Furthermore, we did an experiment with classification. We found out what's applicable, what's not applicable, built in, yes, no decisions, so binary, right? Filter for variable profitability only, and risk management, go, no-go decisions. That's it, guys. In a nutshell, that's how we can open new Starbucks restaurants. I had initially called it open 10 new Starbucks restaurants, is way more than 10 here, okay? But we can refine that. We can filter down. We can open restaurants making over 218,000 or 200,000 a year and over. So that's an easy fix. But definitely a good baseline for comparison. It's a good starting point for a conversation. And we have a ton of information here where we can move forward and set up some intelligent, very informed, very meaningful conversations with our colleagues, and then push this over the goal line, past the goal line, and get over the finish line, and get to the next step and start, start pumping some money into these scenarios and into these real estate investments, and start building up some hardware and some stores and some outlets to do transactions with our coffee consumers. Okay, so that's it, guys. I wanted to share my findings. Hopefully that's useful, informative, and relevant, and motivating and stimulating, and all these great things. I did this analysis a couple days ago. I wanted to share my findings with you. There you go. I am going to export this file as an HTML format. Okay, and I'm going to save that down, and I will share all my findings with you a little bit later when I drop the video a little bit later today. You'll have everything you need, share all the code with you, and you'll have that when I drop the video in a couple hours. Got to go pick up my kid from his camp. When I come back from that, I'll post a video on YouTube. There you go. Let me know if you have questions. Hit the like button, subscribe if you haven't done so already. And yeah, post some comments in the comment section. Let me know your thoughts. I think the accuracy of this analysis is spot on. If you find a deficiency, or I missed something, or something was calculated incorrect, let me know about that. I don't make too many mistakes, but I have made some mistakes in the past, and people brought that to my attention. I fixed it. That only happened once in the past year or so, but I fixed it and made it right. And that was it. So share your thoughts, your opinions. Love to hear about it. Thank you so much for your time, and I'll see you guys soon in the next video when I post that, probably in a day or two. So talk to you soon. Goodbye. Goodbye for now.